Good morning, class. We are looking at section 3.11 hyperbolic functions. Okay, so we are going to look at hyperbolic functions as the last section in this chapter. So we looked at differentials, okay, and the idea of delta y versus dy, okay, and then how f of x plus delta x is precisely f of x plus delta y can be approximated by this. And when we say linearization, we simply mean find the equation of a tangent line. And as long as the graph is concerned, this is delta x, or run. This is delta y. That means rise along the curve y equals f of x, and dy, which is AB, rise along the tangent line. Hyperbolic functions, okay. Certain even and odd combinations of the exponential functions e to the power of x and e to the power minus x arise frequently in math, okay. They have the same relationship to hyperbola that the trigonometric functions have to the circle. Everybody remembers that x squared plus y squared equals 1. This is the unit circle, right? And then cos squared minus sinh squared equals 1. That's the relationship between sinh x and cos x, okay? And that gives rise to the name hyperbolic functions, okay? And there are these definitions that hopefully you remember from pre-calculus. So let's discuss cos x. I hope you remember that cos x by definition is e to the power of x plus e to the power minus x over 2. This is the definition of hyperbolic cosine, also called cos x. Sinh x, the same thing, you put a negative in between. These two are definitions, class. Then, following the trigonometric functions, we define the following. Hyperbolic tangent. Remember, tangent was sine over cosine, so hyperbolic tangent is sinh over cos. Cotangent was cosine over sine, so it's hyperbolic cosine over hyperbolic sine, or we can say 1 over hyperbolic tangent, okay? 1 over hyperbolic tangent. That's another way of writing it. Cosecant was 1 over sine, so hyperbolic cosecant is 1 over sinh. Secant was 1 over cosine, so hyperbolic secant is 1 over cos. So very similar to trigonometric functions and identities. There are some similarities, there are some differences. We're going to discuss all of those. Okay, so the hyperbolic functions satisfy a number of identities that are similar to trig identities. So for example, sinh, I hope you remember that sine of minus x is minus sine x, okay? Cosine of minus x is cosine x. In other words, every function was odd with the exception of cosine and secant. You remember that? So that's the idea. Sine of alpha plus beta, now we are looking at sinh x plus y, okay? Now, sine of alpha plus beta was sine alpha cosine beta plus cosine alpha sine beta. It works exactly the same way here. For cos, however, if you remember, it was a negative here, class. Cosine of alpha plus beta was cosine alpha cosine beta minus sine alpha sine beta. So let me just write that for you. So I want you to remember, for example, there are some similarities, there are some differences. Cosine, and I don't want to use x and y on purpose because I want you to see this is cosine. Cosine of alpha plus beta was given as cosine alpha cosine beta minus sine alpha sine beta. I hope you remember that. So there are a lot of similarities between the identities that you find here and the identities we found in the case of trigonometric functions. Okay, so those are some identities, okay, that are similar to what we have seen. Another example, look at, for example, sinh. 2x. You remember sine 2x was 2 sine x cosine x. So that works almost the same. Okay. So now this is another difference. Cosine of 2x was cosine squared x minus sine squared x. So that's the difference, class. Okay. In any event, and now the derivatives. Okay. The hyperbolic derivative functions. Okay. How do you differentiate it? Just as an example, I want to differentiate sinh. I don't know the answer, everybody. I don't know the answer. So I'm going to differentiate its definition, e to the power of x minus e to the power of minus x over 2. That we can do. I hope you realize this means 1/2 e to the power of x, okay, class? So the derivative is itself. And this means, so if you want, I can rewrite it so if it helps you see. So this is the same as saying dx of, this is 1/2 e to the power of x minus 1/2 e to the power of minus x. So you're differentiating that, okay, piece by piece. So when you differentiate that, this gives you itself, this gives you negative 1/2 times negative becomes plus 1/2 e to the power of minus x. So this becomes plus because of this negative. And so you end up with this. Now, what is this? This is the definition of a cosh. Okay, so remember the derivative of cosine was negative sine, but that's not the way it works here. This is another example which is different. So the derivative of sine was cosine, so the derivative of sinh is cosh. The derivative of cosine was negative sine, but over here it's sinh. And the proof is very simple. I highly recommend you do this. Use the right side here and prove it. You can easily come up with the answer. The rest are similar. The derivative of tangent was secant squared. Now hyperbolic tangent is hyperbolic secant squared. Okay, the derivative of hyperbolic tangent is the hyperbolic secant squared x. For cotangent was negative cosecant squared. It works almost the same. Now these two, for the secant, it doesn't work. It was positive. If you remember the derivative of secant, okay, just to remind you, a couple of differences. So for example, the derivative of secant was secant x tangent x, whereas here we have a negative sign. Okay, class. So that's the difference, and this is another one. Let's just write that also. The derivative of cosine was negative sine, okay, but here it's both positive. So, and again, we proved this one. You can prove the rest of it accordingly, okay? So we will look at maybe a couple more proofs, but it is important for you to see how you can go use the definition and prove it. Now, one of the things I want to mention is about the graphs again. The general idea about the graphs, remember, first, let me just graph a couple of things for you. Everybody remembers. This is y equals e to the power of x, okay? Of course, we want half of them then. This would be this is not to scale, class. Y equals e to the power of minus x. And then if we put a minus in front, let's call this y1, y2, y3. So those are the graphs, and then you can apply the 1/2. So I hope you see, because of the shape of those, we can easily figure out if we combine something like sinh, which is e to the power of x minus e to the power of minus x squared, becomes something almost looking like y equals x cubed. This looks like y equals x squared shifted up by 1, okay, and the rest accordingly. So you don't have to worry about the graphs. You have to know roughly how the sinh looks like. Sinh looks like y equals x cubed, and cosh looks like y equals x squared, that it's shut up by 1 unit. Okay, so that's the idea. But anyways, you're exposed to the graphs in case. We want to prove that cosh squared minus sinh squared equals 1. We don't know that, so all we know is this. Okay, so in order to prove that, remember what we did in trigonometry. We started with the more complicated side. The more complicated side is the left side. So replace the cosh with what you know, replace the sinh with what you know. That means square the first one minus square the last one. Now, it's just a matter of keeping proper accounting, okay, doing elementary algebra. If you square this one gets squared up to the power of 2x. Then 2 times the last, 2 times e to the power of x times e to the power of minus x becomes positive 2, and then plus e to the power of minus 2x over 4. The same thing happens here. The only thing I want to make sure everybody understands what's happening here, because some people may have a difficult understanding how we came up with 2. This is 2 e to the power of x, e to the power of minus x, okay? Again, we are using a plus b squared, which is a squared plus 2ab plus b squared. So I'm using that identity. So when I square this one becomes e to the power of 2x. Now 2 times the first times the last, 2 times the first times the last becomes this. E to the power of x and e to the power of minus x, they give us e to the power of 0, which is 1, so 2 times 1. And then this one to the second power is this, the rest follows. Now you apply the negative sign, okay? I hope you see that when you apply the negative sign, this becomes negative, cancels this one. This becomes negative, minus and minus b plus 2 and 2 is 4, or 1. I hope everybody is okay with combining those two. Okay, class? So you apply the negative. So I hope everybody is fine with that. All right. Let's prove this identity. 1 minus hyperbolic tangent squared is hyperbolic secant squared. Now let's go back to the trigonometry. When we did the Pythagorean identity, sine squared plus cosine squared was 1. And then there, okay, just quickly refreshing your memory, class, we did, okay, remember sine squared plus cosine squared was 1. Tan squared plus 1 was secant squared. And cotangent squared plus 1. Maybe I should say 1 plus cotangent, because I want to make a point what we did over there. 1 plus cotangent, not that it matters. 1 plus cotangent squared is cosecant squared. So what did we do? Okay, we had this, okay. When we divided both sides by cosine squared, we proved this one. When we divided both sides by sine squared, we proved the next one. So we do exactly the same thing here. What is this one? We don't know. We already have the first one, right? This is Pythagorean identities that we have for trigonometry, and this one we just proved. So let's use that one. So we're going to start with that. And remember what we want. We want 1 here, right? So how do you get that? Divide by the first term, which is hyperbolic cosine squared, both sides. So let's divide. And when you divide, practically you're done. This becomes 1. This becomes minus hyperbolic tan squared. And this is 1 over cosh squared, so hyperbolic secant squared. So it's fairly simple, okay? Let's look at more proofs, and some of this we have seen it in a pre-calculus class. Okay, I want you to remember that we've done this. Okay, so I hope you remember some of it from the pre-calculus. So we want to prove this is the case. So again, we don't know that. We go with what we know, and we're going to replace the x here with negative x. So cosh of negative x, you go here, replace this with negative x, and as you can see, this becomes e to the power of negative x, and this becomes e to the power of x, okay? And that's the same as this one. Take a look, compare. These two are identical. Therefore, we proved they are the same. So time, here, replace the x with negative x, and we have the proof. So I hope everybody is clear as to how we arrive at it, okay? So that's pretty straightforward. We are going to go to the next one. Again, how do we do the next one? Just the way it's given class, we don't know the answer. We look at the side, okay? We want to find cosh of x plus y equals cosh x cosh y plus sinh x sinh y. Again, we don't know if this is the case. To prove it, we start from one side, and one side that is more complicated is the right side. This is what we did in trigonometry. I hope you remember that. Okay, everybody? So using the trigonometry, idea, we can figure out what to do. So cosh x, replace it. Cosh y, replace it. Sinh x, sinh y. So I hope everybody can see that what we are doing here, and my assumption is everybody knows how to do the algebra behind this. Okay, class? So multiply. Okay, so this is cosh x, this is cosh y. I hope you see that. So when we multiply, this becomes e to the power of x plus y, this becomes e to the power of x minus y, so on and so forth. So we are multiplying. So let's do that. I'm assuming everybody can multiply. Everybody has an easy time with multiplication. So having said that, what happens next? The denominator is 4, okay? The denominator is 4. Let's cancel out what we can. Those two cancel out, everybody. Those two cancel out, okay? And whatever is left, we have 2 of each. So we can factor out the 2, okay? Which means 2 goes away, this becomes 2. And I hope you see it looks like cosh of x plus y. So that's a proof, believe it or not. Okay, class? All right, let's look at more proofs. We want to prove this. So we want to go again from the more complicated side to the less complicated side. We're going to start with the left-hand side. And the left-hand side, I hope you remember when we were proving things in trigonometry in the beginning, or anytime we started dealing with tangent, cotangent, secant, cosecant, we figured, well, let's go with sine and cosine. So we can do the same thing. Let's go with sinh and cosh. So we are going to go with the left side and replace this with sinh and cosh. To do that, this is a complex fraction. If we multiply the top and the bottom by cosh, we go to a simple fraction. Cosh times 1 plus this cancels out plus sinh. Cosh times 1 minus, and the same. So far, so good. So this is cosh x plus sinh x. And why are we doing that? So now we know what is cosh x. We know what is sinh x. So we are going to plug in, everybody. We are going to plug in what? The definition of a cosh as well as the definition of a sinh. Let's do that. the definition of a cosh and sinh. And so take a look at the top. Okay, this one cancels out this one. Okay, over here, because of this negative sign, this one cancels out this one. Again, I'm assuming everybody can see what happens. The top is easy to see, the bottom class, this minus, okay, if you go here, this makes this minus, this makes this plus, okay? If you extend this, this makes this plus, okay? And so these two cancel each other, the other two cancel each other, and it becomes e to the power of x over e to the power of minus x, which is e to the power of 2x. I hope you can see that, class. This is e to the power of x over e to the power of minus x. And this is e to the power of 2x. All right. If hyperbolic tangent is 12 over 13, can we find the rest of it? Okay. And hyperbolic tangent is positive, okay? And by the way, if you look at the graph, all of them become positive simply because if the hyperbolic tangent is positive, that means x is larger than or equal to 0. Okay, in fact, x is larger than 0 because at 0 is 0. So x is larger than 0. So hyperbolic tangent is that. So quickly, hyperbolic cotangent is the reciprocal of that. So first we have to know that x is larger than 0. So take a look at the graph and it tells you. So hyperbolic tangent is given, hyperbolic cotangent is the same thing, flip it over. Then if we use this identity, we can find hyperbolic secant. So we use that. I'm going over this pretty fast because I want to get to the bottom of this, chapter class. I want to make sure that we are done with that. So it's a simple case. You calculate this and there are two answers and you keep the positive for the same reason that was mentioned here. So now that you have hyperbolic secant, practically you have everything. For example, cosh squared minus sinh squared will give you cosh. Okay. And to find sinh, there are different ways of approaching it. One is that you use the identity with the cosh squared and sinh squared. The other one is that hyperbolic tangent is sinh over cosh. Okay, class? And you can find it that way. And of course, the reciprocal of that. So I hope everybody is okay with this. Let's do a little bit of a differentiation, class. Let's do a little bit of a differentiation, fairly easy questions. Sinh, you can ignore that. Again, the way we read the trigonometric functions, sine and we stop, sinh and stop, sinh, stop. What is the derivative of a sinh? Is cosh. So it's cosh 10x squared. Okay, so cosh 10x squared, and then times the derivative of this, which is 20x, we put that in front. Okay, so perhaps you want to do this. You want to say this is cosh 10x squared, and then times 20x, and 20x sits in front. Okay. For the next one, the derivative of cosh square root of x. Okay. Now again, you want to read this cosh. What is the derivative of cosh? Sinh. So sinh square root of x, and then Square root of x, the derivative is 1 over 2 square root of x. By now, we have enough practice. I'm assuming everybody knows this, okay? So the derivative of a cosh is sinh. Okay, everybody, cosh is sinh. And then by the chain rule, the derivative of square root of x, and there you have it. Okay. Now, hyperbolic tangent. I don't even mention this. Hyperbolic tangent is hyperbolic secant squared. So stop this one. So hyperbolic secant squared of the same thing by the chain rule times the derivative of the parentheses, which is e to the power of 2x times 2. So again, this gives you this. You write the same argument, and then you need the derivative of this argument, which is e to the power of 2x times 2. You just rewrite it. You just rewrite it, class. Okay. Let's look at this one. Hyperbolic cosecant t times 1 minus natural log of hyperbolic cosecant t. All right, let's see how it's done. This is using the product rule. So first look at this piece in blue. Hyperbolic cosecant. Hyperbolic cosecant is negative cosecant cotangent, okay? So negative cosecant cotangent times the second piece. Now, second piece, you want to take the derivative minus, okay? Minus. Now, natural log. The moment you see natural log, you flip this over. So 1 over this piece minus 1 over this piece. And what is the derivative of hyperbolic cosecant? Is negative hyperbolic cosecant times cotangent. And then by the product rule times the first piece, okay? So let's quickly look at that. The derivative of this piece is this piece and times this. Done. Minus, okay, the derivative of this piece is minus 1 over, okay, flip this over, flip this over, flip this over, okay, times the derivative of the inside, which is this, by the product rule times the derivative of the first piece. You're done with calculus. We are going to simplify, class. Simplification means we are going to distribute this 1 times 1 is itself minus hyperbolic cosecant cotangent. And then this piece times this is plus, okay, plus everybody, okay, hyperbolic cosecant, hyperbolic cotangent, ln of hyperbolic cosecant, okay. Now for this one, they cancel each other and this becomes positive. So take a look at what happens. These two cancel each other. We're going to write this. So these two cancel each other. Now these two are, if you look at the first one and the last one, they are just opposite. This is negative, this is positive. They cancel each other. So only the middle term is left. And this is the final answer. And this is the final answer. So we are done with hyperbolic functions and their derivatives. We look at inverse hyperbolic functions next.